Okay, let's continue. Let's see what we get actually if we expand the equation in R. I'm going to anticipate a little bit and I'm going to tell you that in the end, the Sturm-Liouville problem will be the H equation. So we'll see that later when we actually get to solve the PDE. But for now, let's focus on what we get for the equation in R, and let's see if we can handle that. And then we're going to analyze the remaining equation in theta, which you'll see leads to the so-called Legendre equation. So the equation in R, if you take it separately, so we have minus R, and actually let's do the expansion here. Let's do the derivative. So we do it once, the product rule, so 1 times big R plus R times R prime of R, and then one more time, and then that's going to be equal to minus lambda R of little r. Remember, for convenience, we can, at this point, just write R for big R of little r, and by the same token, we can write big H instead of H of theta, just for convenience, because now there's no risk of confusion. Sometimes I just emphasize theta when it's needed, but whenever it's not a problem and there's no risk of confusion, you can always drop the specification of the variable for each of them. So one more product rule here, we have minus r, one more derivative, so that's going to be r prime here, and another product rule for this term, 1 times r prime plus r big R double prime. And let's rearrange the terms. What do we get? Let's rearrange the terms and then move them to the right-hand side. So I'm going to have minus r squared r double prime. On the other side becomes r squared r double prime. Then I'm going to have, this is 2r prime, right? So to the other side, that becomes plus 2 little r prime minus lambda r equals 0. So pause for a moment and realize that you know how to solve this. This is a Cauchy-Euler equation. Right? So the dependent variable is big R. R double prime has R squared attached to it. R prime has little r attached to it, and big R by itself. So this fits the framework A x squared y double prime bx y prime plus cy equals 0. So remember, we solved that using the characteristic equation, ar squared b minus ar squared r, and then plus c equals 0. I suppose you probably shouldn't use little r for the characteristic equation, because now little r is a variable in the problem in the PDE. But anyway, when we get to solving this again will be something that you know how to handle, right? Just the Cauchy-Euler equation. But because this is not the Sturm-Liouville problem, you got to do the equation in H first, and then for each eigenvalue, for each lambda, you're going to solve the corresponding equation in R for each lambda. So let's focus now on the main hurdle, right? I mean the equation in H. And let's just do a little bit of more algebra to write it in a more compact form. So the equation in H, right, if I multiply by big H, becomes 1 over sine of theta H prime of theta prime again minus lambda H of theta. And again, let's take the maximum domain for theta, right? Theta between 0 and pi. And just to remove this annoying fraction here, let's multiply both sides by sine of theta and then move everything to the left side. This is going to be basically your standard format for the Sturm-Liouville problem. All right, so it's worthwhile to basically mark it down and have it in your mind, because for many problems, you're not going to do these steps all over again. So once you do a steady state temperature in spherical coordinates, you can start with this and with this, right? I mean, once we went over this process once, you don't have to do it one more time. So this will be the equation in H. And if you're curious whether this is a complicated equation or not, you can enter this in Maple, and you'll see that Maple will make Wolfram Alpha. It'll give you some weird series formats for the solution, probably involving the word Legendre, which is a sign that this, just like the Bessel equation, doesn't have solutions in the closed form given by elementary functions. So the solution is in a series form as well. It is more practical to analyze a associated equation to this one, which actually constitutes the standard Legendre equation. Because if you use a clever substitution, some of these coefficients will become easier, and the equation, the standard equation to deal with, is much more compact. So let's do the substitution and then finally end up with what constitutes the standard Legendre equation. So because of this domain for theta, and remember, if you look at trigonometric functions, right, I mean, if theta is between 0 and pi, the cosine corresponding to this range is going to be between -1 and 1. So let's make the substitution, which you will see it will simplify the equation quite a lot. Let's make the substitution x equals cosine of theta. So pay attention to the relationship between the domain of theta and the domain for x. That's very important for later to understand how the process goes. If I take the maximum domain for theta, which is 0 and pi, the maximum domain in spherical coordinates, of course, then the domain for x is going to be -1 and 1. Cosine of 0, 1, cosine of pi -1, right? So overall between -1 and 1. This is the reason why when we solve the Sturm-Liouville problem related to this equation, when we make this change of variable, the default domain is -1 and 1, although again this can be changed if we don't have a full sphere. So if you have a different object, right? I mean, a portion of the sphere or a wedge of a sphere. So let's see what happens if we make the substitution and how we rewrite this in terms of x. So instead of a function in theta, let's think of h as a function in x. And if we make this substitution, at some point I'm going to need to compute dx d theta. So let's rewrite the equation with the d theta notation, because the chain rule that I have to use at some steps, it's going to be easier to follow if I use the differential operation notation. So the exterior derivative is d with respect to theta, right? So the derivative with respect to theta, and inside I have sine of theta dh d theta. And now let's do the substitution. If you treat big H as a function of x and then as a function of theta, then because of the chain rule, dh d theta can be written as dh dx times dx d theta. Now dx d theta, notice here carefully, is going to be minus sine of theta and then dh dx. So dx d theta is minus sine of theta dh dx. Furthermore, inside this derivative I have sine dh d theta. So if I multiply this by another sine, I get that sine of theta dh d theta is minus sine squared of theta dh dx. And that's very convenient because I can write this in terms of x. Now remember, sine squared is nothing but 1 minus cosine squared. And because of my substitution, I can replace cosine squared with x squared. And so that's going to be minus 1 minus x squared quantity dh dx. Okay, let's leave that minus on the outside. You'll see later why. And one more thing we have to do, it's yet another chain rule of the same type. Because remember, in the equation that I have to deal with over here, sine dh d theta is differentiated one more time with respect to theta. So we're going to do another chain rule of the same type. We're going to do again the derivative with respect to theta of minus quantity 1 minus x squared dh dx. And so that's the derivative with respect to x of the inside times dx d theta, which is again another minus sine of theta. So that's minus sine of theta, and notice now these minus cancel out. Okay, so when everything is said and done, what you end up with here is basically the derivative with respect to x of 1 minus x squared dh dx times the sine of theta on the outside. Now that sine of theta will disappear when I plug it in back into the full PDE, full equation in H, which is the reason why we made the substitution in the first place. All right, so if you want to pause and retrace the steps for a moment, again, you don't have to do this one more time once we do it once, but just for practice, make sure you understand all the steps. So at this point, we're going to treat big H as a function of x via this substitution. And when we plug it back into the equation for H, sign will cancel, as you'll see immediately. So we're going to have, so when I replace this with this, we're going to have the derivative with respect to x, 1 minus x squared dh dx, and sine of theta on the outside, plus lambda sine of theta big H of x. So now we think of big H as a function of x equals 0. So if we divide by sine of theta, sine cancels. Again, we assume theta is between 0 and pi, which means sine of theta is not equal to 0, so we can cancel it out. And then we arrive to an equation in x. So let's actually do the following, the remaining part of this part, so to speak. I mean, in another page, I want to put these two side by side and then define finally what constitutes the standard Legendre equation. So we have basically the equation in H that comes from the PDE itself, right? Or from the separation of variables. So the equation in H will be a second order linear ODE in H, and it's going to have the form sine of theta, see H prime of theta, and another prime on the outside, plus lambda sine of theta, big H of theta equals 0, with theta between 0 and pi. After we make the substitution x equals cosine of theta, this leads to the equation in x, which is given by 1 minus, so now we can use the prime notation again, because now we treat the big H as a function of x. 1 minus x squared H prime of x prime plus lambda big H of x equals 0, where x is between minus 1 and 1. So these are equivalent via this substitution. All right, what constitutes the Legendre equation is this, basically. So now we can write the definition. The Legendre equation is defined as, and remember, just for standardization, we denote in this case the dependent variable as y, right? I mean y of x, just to make a standard formula, so to speak, because again, in various problems you will have different notation. So the Legendre equation is defined as 1 minus x squared y prime, and then prime on the outside, plus lambda y equals 0, where y is a function of little x, so x is a dependent variable, and this may vary, but in this case, x is between -1 and 1. So the Sturm-Liouville problem that comes from the steady state temperature in spherical coordinates happens to be a Legendre equation. So the Sturm-Liouville problem for steady state temperature in spherical coordinates is a modified, let's call it this way, is a modified Legendre equation. I'm going to call it modified because it's via this substitution that you have Legendre equation, right? So when we study the Legendre equations, we're going to start with this type of equation. But the connection with the actual steady state temperature is via this substitution. All right, so once you end up with this, via this substitution, one ends up with the so-called Legendre equation. Again, we don't have to do this substitution all over again. Suffices to say, and this is again an important remark, if big H of x is the solution of 1 minus x squared h prime prime plus lambda big H of x equals 0, then h of cosine of theta will be the solution of what we actually have in the PDE, sine of theta h prime, prime one more time, plus lambda sine of theta big H equals 0. So all we have to do once we know how to solve the Legendre equation is to plug in theta for x. And for convenience, of course, we're going to derive formulas in terms of theta already. You can pick at the formula sheet, but you know that's the connection between these two. So with that in mind, I'm going to add another part to illustrate how the solutions of the Legendre equations are obtained, and I think that's enough for our first lecture. Let me point out before we move on to the last part that this is still a linear ODE of second order. Now you may wonder why it's given in this prime of prime notation. This is just for convenience to make it more compact. I mean, if you really want to, you can expand this derivative, right? So I mean, you can differentiate, do the product rule. So it's minus 2x y prime plus 1 minus x squared y double prime plus lambda y equals 0. This, you know, is less compact, so that's a more traditional or more compact way of writing it down. But it's important to point out that this is still linear, homogeneous, second order ODE. And what does that mean? If you remember what we studied in ordinary differential equations, it means that y, the general solution, it's still a linear combination of two independent solutions. So when you look for a general solution of the PDE, I keep on saying PDE, sorry. So if you look at the general solution of this second order ODE, you're still looking for two independent solutions. So have that in mind as we move along on the last part to explain how the solution is obtained. Unlike the Bessel functions, actually it's a little bit easier to see how these series solutions are obtained when you try to solve the Legendre equation. So that's it for this part, and we're going to continue with the next one in a minute.